Every second, an overwhelming volume of untamed, raw energy bombards our planet from space. But catching that light is only the first problem. When a blackout hits your neighborhood, the logical assumption is that having solar panels on your roof guarantees your lights stay on. You trap the sunlight right above your living room, so you should have an automatic backup. But catching that light means trapping it at the subatomic level, forcing negative charge to one side of a crystalline silicon panel and positive to the other. This produces direct current, or DC. Unbound DC power is completely incompatible with an unpowered grid. Without a functioning utility network to receive and regulate that current, the raw energy flowing off a roof becomes a chaotic liability. A localized power failure quickly escalates into a severe physical hazard. This schematic illustrates a scenario known as accidental islanding. The solar-equipped home actively pumps excess, unmonitored electricity backward into a severed power grid. This creates an immediate, lethal threat for utility crews dispatched to repair these lines, who assume the grid is entirely de-energized. Beyond the danger to human life, this uncontrolled flow of electricity bypasses the local step-up transformers, sending mismatched power directly into municipal grid infrastructure and causing severe physical damage to the local network. To prevent a neighborhood from turning into a lethal island, the solar inverter, the specific device acting as the bridge between the sun and the transmission lines, must instantly recognize that the grid has failed and sever the physical connection. The inverter mathematically sculpts raw DC energy into a smooth alternating current sine wave. Sophisticated microcontrollers monitor the grid's rhythm, adjusting output so amplitude and phase angle precisely match the network. This continuous listening acts as a passive defense mechanism. This regulatory document outlines the IEEE 1547 standard, which dictates the specific safety thresholds. If the inverter detects grid voltage or frequency drifting outside these designated limits, it is required to shut its output down instantly. During a standard blackout, the utility voltage drops entirely. The inverter registers this massive drop. Its passive monitoring trips the safety protocols, and the system shuts off. Passive observation works flawlessly for total disruptions. However, relying purely on listening to the grid leaves the inverter exposed to one specific, highly dangerous blind spot. Electrical engineers call this rare vulnerability the non-detection zone. If solar panels generate the exact power the home consumes, local voltage and frequency stabilize. Monitors read this perfect balance, assume the grid is functioning, and keep the connection open. To fix this, the inverter injects a microscopic frequency nudge. An active utility grid is massive enough to effortlessly absorb that tiny disturbance. But if the grid is severed and dead, that pulse immediately destabilizes the local frequency, forcing the inverter to trip its safety shutoff. Keeping the lights on with solar during an outage does not happen by accident. It requires specific, intentional engineering. This map illustrates the required hardware: an automatic transfer switch, a hybrid inverter, and local battery storage. When the main grid fails, the transfer switch physically severs the external connection. The hybrid inverter then seamlessly routes AC power inward to the home and battery. By trapping the power inside this closed loop, the home creates an intentional island, safely powered and entirely harmless to the repair crews working on the streets below. Generating reliable modern energy requires catching a photon at the end of the 150 million kilometer journey, driving it through quantum physics to sculpt its raw power, and actively pushing against the grid to constantly test for vulnerabilities. Safely harnessing the sun means matching the grid's rhythm flawlessly, but also knowing exactly when to let it go.